So you know how we always sort of picture the early universe? Like right after the Big Bang?
Yeah.
It's like this massive opaque void.
Right, yeah, totally.
But get this, the James Webb Space Telescope, JWST, has taken a look back at that, like dawn of time, and spotted something amazing.
Oh, really?
A whole galaxy shining through what should have been a thick cosmic fog. It's pretty wild. We're taking a deep dive today into the discovery of this galaxy called JADES GS-Z13-1.
Okay, Jade's G is Z13-1.
Yeah, and it's an incredible observation because it shows us this galaxy as it existed just 330 million years after the Big Bang.
Wow, so early.
Crazy early, right?
Yeah.
For this deep dive, we're going to be looking at NASA's reports on this discovery, as well as some insights from the Cosmic Frontiers Astronomy podcast.
Cool.
And one of the things that both of these sources really highlight is that this discovery, well, it kind of throws a wrench into what we thought we knew about the early universe.
How so?
Well, the early universe was filled with this fog of neutral hydrogen, and this fog made it really difficult for light to travel.
Right.
So the mission for us today, and for you listening, is to figure out why the light from this early galaxy, JADES GS-Z13-1, is so darn clear. Like, how did it manage to bust through that fog?
Yeah, that's a good question. It's like a lighthouse in a dense fog, right? How can you even see it?
Exactly. So first things first, let's talk about this galaxy, JADES GS-Z13-1.
Okay.
So it wasn't just stumbled upon randomly.
Right.
Astronomers found it using JWST's near-infrared camera.
NIRCam.
Yes, NIRCam. As part of the survey called the James Webb Space Telescope Advanced Deep Extragalactic Survey.
That's a mouthful.
It is. It's JADES for short.
Okay, Jade's.
And this survey uses this technique called deep imaging, where it's basically like leaving the camera shutter open for a really long time to capture the faintest light from really far away objects.
I see. So it's kind of like those long exposure photos you see of the night sky, where the stars leave those streaks of light.
Yeah, exactly like that, except on a much, much grander scale. And like we said, this galaxy is super far away.
Yeah, you mentioned 330 million years after the Big Bang, which is
incredibly early in the universe's lifetime.
It's like almost the very beginning.
Almost. The universe is about 13.8 billion years old, so we're talking about seeing this galaxy as it was when the universe was just a baby.
Wow. And how do they even measure that? How do they know it's that old?
Redshift. It's a measure of how much the light from an object has been stretched as the universe expands.
Redshift.
Right. And the light from JADES GS-Z13-1 has a redshift of 13.0, which means it's one of the most distant objects we've ever observed.
So the higher the redshift, the farther away and older the object.
Exactly.
Got it.
And this is where the James Webb Space Telescope really shines.
Literally.
Yeah, literally. So the light from these super distant objects, it gets stretched out or redshifted into the infrared part of the electromagnetic spectrum.
Okay.
And JWST is specifically designed to observe infrared light. It's like it has infrared vision.
I see. So it's perfectly suited to look at these early galaxies.
Exactly. And on top of that, it's located in this perfect spot for observation.
Oh, right. It's not actually orbiting Earth, is it?
Nope. It's stationed at what's called the second Lagrange point, or L2.
L2.
It's about 1 million miles away from Earth, which gives it a clear view of the universe without any interference from Earth's atmosphere.
So it's like it has a front row seat to the cosmos.
The best seat in the house.
So JWST has NIRCam for capturing images of these distant objects.
Yes.
But you also mentioned something about spectroscopy.
Right. So NIRCam captures the initial images, but to really understand what we're seeing, we need to analyze the light in more detail, and that's where spectroscopy comes in.
Gotcha.
JWST has an instrument called the Near-Infrared Spectrograph, or NRSpec.
NRSpec.
And NRSpec basically acts like a prism, splitting the light from the galaxy into its individual wavelengths.
Like a rainbow.
Exactly. And by studying these different wavelengths, scientists can figure out what the galaxy is made of, how hot it is, and even how fast it's moving.
Wow. That's incredible. So like a cosmic fingerprint.
Perfect analogy.
So NIRCam spots the galaxy, and then NRSpec analyzes the light.
Yes.
And that's where this whole mystery of the missing fog comes in, right?
Exactly. The analysis of the light from JD's GSZ13-1 revealed something really unexpected.
What's that?
A strong signal of something called Lyman alpha emission.
Lyman alpha emission. Now that sounds familiar. Remind me what that is again?
Of course. So Lyman alpha emission is a specific type of ultraviolet light. It's emitted by hydrogen atoms when their electrons jump from a higher energy level to a lower one.
Okay, I'm following so far.
Now remember that fog of neutral hydrogen we talked about?
Yeah, the one that should be blocking all the light.
Right. Well, neutral hydrogen is really good at absorbing Lyman alpha emission.
So if the early universe was filled with this fog,
We shouldn't be seeing any Lyman alpha emission from JADE's GSZ13-1.
but we are.
But we are. And that's the mystery.
It's like seeing a bright light through a thick fog. It doesn't make sense.
It doesn't unless the fog had somehow cleared around this galaxy.
Interesting.
And this leads us to a really important period in the history of the universe called the epoch of reionization.
Reionization. Okay, break that down for me.
So for a long time after the Big Bang, the universe was in this era called the cosmic dark ages.
Dark ages. Sounds ominous.
It was dark because the universe was filled with this neutral hydrogen fog, which blocked most of the light.
Okay.
But then the first stars and galaxies started to form. And these early stars and galaxies emitted a lot of ultraviolet radiation.
Right.
And this radiation started to ionize the neutral hydrogen.
Ionize.
Basically, it stripped the electrons from the hydrogen atoms.
Oh, okay.
And this process of ionization gradually cleared the fog, allowing light to travel freely. And that's what we call reionization.
I see. So the universe went from being foggy to transparent. And this discovery of the Lyman alpha emission from JADE's GSZ13-1 suggests that reionization might have happened earlier than we thought.
That's right. Because if we're seeing Lyman alpha emission from this galaxy, it means that the region around it must have already been reionized. And this galaxy is so early in the universe's timeline that it suggests reionization might have started earlier than our models predicted.
Wow, so this little galaxy is shaking up our understanding of the early universe.
Big time.
So what could have caused this early reionization around JADE's GSZ13-1?
That's the million-dollar question. And there are a couple of leading theories.
Okay, let's hear them.
One possibility is that JADE's GSZ13-1 contained a population of very special stars called population 3 stars.
Population 3 stars. What's so special about them?
These were the very first stars to form in the universe.
Oh, wow. Like the pioneers.
Exactly. And they were different from the stars we see today. They were much more massive, hotter, and luminous.
So they were like superstars.
And they would have emitted a ton of ultraviolet radiation, which could have been enough to reionize the hydrogen around them very quickly.
So these population third stars could have been the fog busters.
Precisely.
That's a cool idea.
Right.
What's the other theory?
The other possibility is that JADE's GSZ13-1 had an active galactic nucleus, or AGN, at its center.
An AGN. What's that?
An AGN is basically a supermassive black hole that's actively feeding on matter.
A black hole gobbling up stuff. That sounds intense.
It is. And as this matter falls into the black hole, it gets superheated and releases a lot of energy, including ultraviolet radiation.
So an AGN could also have contributed to the reionization.
Exactly. It could have been powerful enough to clear out the fog around JADE's GSZ13-1.
So it's either superstars or a supermassive black hole. Or maybe both.
It could be a combination of factors. Astronomers are still analyzing the data to figure out exactly what's going on.
It's like a cosmic detective story.
Now, earlier we talked about redshift and how it tells us the distance and age of an object. Can you explain a little bit more about how redshift works and why it's so important for studying the early universe?
Sure. So imagine a light wave traveling through space.
Okay.
As the universe expands, the space between objects stretches, and this stretching also affects the light waves.
Okay.
The wavelengths get longer, which shifts the light towards the red end of the spectrum. That's why we call it redshift.
I see. So the more the light is stretched, the farther it has traveled.
Exactly. And the farther it has traveled, the older the light is.
So by measuring the redshift of an object, we can determine its distance and how long ago the light we're seeing left that object.
Right. And in the case of JG's Z13-1, that redshift of 13.0 tells us that we're seeing this galaxy as it was just 330 million years after the Big Bang.
Which is mind-bogglingly early.
Totally mind-boggling.
And JADE's GSZ13-1 isn't the only galaxy we found at these extreme distances, right? There's also JADE's GSZ14-0.
That's right. JG's GSZ14-0 has an even higher redshift, which means it's potentially even older than JADE's GSZ13-1.
But JWST 13.1 is special because of that strong Lyman alpha emission.
Right, that's what makes it so intriguing. It's telling us that something unusual was happening in the early universe, something that we didn't expect.
So what are the big implications of this discovery? What does it mean for our understanding of how the universe evolved?
Well, for one thing, it challenges our existing models of galaxy formation. We didn't expect to see galaxies this bright, and this evolved so early in the universe's history.
So our understanding of how quickly galaxies formed and evolved needs to be revised.
Yes. And it also suggests that reionization might have happened earlier than we thought, at least in some regions of the universe.
Right, because if JWST 13.1 had already cleared out the fog around it, then reionization must have been well underway in that region.
Exactly. And this has huge implications for our understanding of how the universe became transparent to light, allowing us to see the stars and galaxies we see today.
It's like we're getting a glimpse into the very first moments of the universe becoming the cosmos we know.
Exactly. And this discovery is just the tip of the iceberg. JWST is going to continue to observe JD's GS-SYN 13.1 and other early galaxies, and we're going to learn even more about the universe's infancy.
It's an exciting time to be studying astronomy.
It really is. We're on the verge of some major breakthroughs in our understanding of the universe.
Well, I'm definitely excited to see what other discoveries JWST makes in the coming years.
Me too.
So, to recap for our listeners, we've been talking about the discovery of JD's GS 13.1, a very early galaxy observed by JWST.
Right.
And what makes this galaxy so special is that it's emitting light that should have been blocked by the fog of neutral hydrogen that filled the early universe.
Exactly. The strong Lyman alpha emission suggests that the region around this galaxy was already reionized, much earlier than we expected.
And this discovery raises some big questions about how galaxies formed and evolved in the early universe and how the universe became transparent to light.
It's a fascinating puzzle, and we're only just beginning to piece it together.
This deep dive has really just scratched the surface of this incredible discovery. If you're interested in learning more, I highly recommend checking out the original NASA article about the findings or the research that was published in the journal Nature.
There's a lot more detail in those sources, and it's well worth the read.
So, as we wrap up this deep dive, I'm left with a big question for our listeners to ponder. What other unexpected discoveries might be lurking out there in the vast expanse of the universe, just waiting to be uncovered?
The universe is full of surprises, and I have a feeling that JWST is going to reveal many more of them in the years to come. And those discoveries might just rewrite our understanding of the cosmos yet again.
And who knows, maybe one of our listeners will be the one to make the next big discovery.
You never know. The universe is a vast and mysterious place, and there's still so much we don't know. But with every new observation, with every new discovery, we get a little bit closer to understanding our place in the cosmos.
And that's what makes astronomy so exciting.
Absolutely.
Thanks for joining us on this deep dive. We'll catch you next time for another exploration of the universe and beyond.
Until then, keep looking up.